Hello, I'd like to welcome everybody to BC Calculus. We're going to start right up in Chapter 3 with extreme values, maxes and mins. Little terminology on the first page. If you have a function and the derivative is either 0 or the derivative does not exist at a certain location, then that location, I called it C in this case, is what we call a critical number. And if you know the point, x comma y, then it's called a critical point. But a critical number is where the derivative is either 0 or the derivative doesn't exist. The reason that critical numbers and critical points are significant is that's where the maxes and mins occur. The thing that you have to watch out for is the endpoints can be a bit snooty. In other words, an endpoint can only be absolute. Endpoints have to be the best or the worst. If an endpoint's not the best max, it's like, well, I don't want to be a max at all. Okay? Showing you some drawings I think will help solidify this. So here are my first couple. I want you to tell me whether the point is either an absolute max, absolute min, relative max, relative min, or neither. I guess you have 5 choices. We're going to start out here alphabetically with A. In A, a lot of people are like, oh, that's local or relative min. And the answer is no, it's not. It's neither. Just hang with me for a moment. I think that'll help out. Speaking of neither, F is also neither. It's not an absolute max because it's not as high as D. It's definitely not a min because the graph was on its way up when it hit F. Same thing over at A. A is not an absolute min because E is lower. And if you back up one slide, you'll see that the endpoints are either absolutes or they're nothing. The critical numbers can be either one. The critical numbers can be absolute, or the critical numbers can be, relative or local. But the endpoints, if you're not an absolute max or absolute min, we have to call you to nothing. And that's what I just did. All right, I think the rest are pretty obvious. You've got an absolute max, and hopefully you're thinking of point D. You have an absolute minimum at E, clearly because E is, lower than anything else on the graph, so it's the absolute min. Same thing, D is higher than anything else. And then B and C become relative maxes and mins. You can also say local. The word local and the word relative are completely synonymous, so I'll just say relative. So B is a relative max, and C is a relative minimum. Over to number 2, we do have an absolute max. It's the highest point that we have, and it's point G. Endpoints, remember, are allowed to be absolutes, but the endpoints refuse to be relatives. They're too good for that. They're too snooty. L is an absolute minimum, which means that H and J are forced to just be relative mins. And you know what I'm going to say, I and K are relative maxes. All right, so again, the endpoints are allowed to be absolutes only. You can have an absolute in the interior, we did here, or the interior points can just be relative or local maxes and mins. All right, moving ahead. Find critical numbers. Again, if you remember from the first slide, a critical number is where the derivative is either 0 or it doesn't exist. All right, so let's take a derivative of this. But before I do, I'm going to rewrite it in a more calculus-friendly form of the 1/2 power over here. And I don't know if you recognize this or not, but it's our longtime friend, the product rule. The x is the u, the quantity part is the v. All right, first derivative. U prime v plus uv prime. Well, u prime is 1, so u prime v will simply be v. U prime v plus u v prime. I have to be careful here. V prime will be 1/2 stuff to the negative half. Uh-oh, times a chain rule, there is a times -1 there. Chapter 2 never goes away. I'm telling you right now, every single day, every single problem, you're going to have chain rules, you're going to have product rules. So if you're not super solid at Chapter 2, please see me. We'll get you shored up a little bit so that you're not going to have that happen to you. All right. Critical numbers. I have to set this mess equal to 0. Before I do, I'm going to factor. I see that we have two terms. Remember, from algebra, terms are separated by addition or subtraction signs. So both of the terms have a 4 minus x in them. I'm going to factor that out. But I'm going to factor out as weird as this sounds, -1/2 of them. Leaving me with 4 minus x to the first. This parentheses and this 1 are completely unnecessary, but I wanted you to see that if you wanted to check yourself. Remember, when you multiply, the powers get added together, the exponents get added, so -1/2 plus 1 does give you the 1/2 you started with. I'm going to go minus, because of this negative right here on the 1, minus 1/2 x. Remember, the parentheses has already been removed by factoring. If you're not sure if you got it right, again, distributed property is the opposite of factoring. Just see if everything comes back, and it does. So we want to set this equal to 0. Well, this looks really messed up. Let me simplify it a bit. I'll turn it into a fraction. The 4 minus x goes into the denominator, and it's a square root down there because of the half power. Up top, I have 4 minus 1x minus another half x. That's 4 minus 3/2 x. Or 4 minus 1.5x. We're going to set that equal to 0. Actually, since it's a fraction, remember, critical numbers can happen when the derivative is equal to 0, or whenever the derivative is equal to, I should say undefined. So once you have a fraction, what you can do is just set the numerator equal to 0. That'll tell you when the derivative is 0. And then once you get done with that, set the denominator equal to 0. That'll tell you where the function's undefined. Those will be critical numbers. All right, let's start up top. So that gives me 4 equals 3/2 x. All right, 3/2 x equals 4. Multiply by the reciprocal on both sides, which of course is 2/3. And you can see that one critical number is x equals 8/3 or 2 2/3. Okay, so that's definitely one of them. And now, if we take that 0 to the denominator, you can also see that x equals 4 would make the derivative not exist. So x equals 4 is also going to be a critical number. Now, some people are like, well, what about 5 or 6 or 7? Because that would give you imaginary numbers. I'm like, that's a great thought. But you don't have to worry about 5, 6, 7, even 4.1, because those numbers you're talking about weren't eligible right from the get-go. They aren't even in the problem's domain. There's a domain for pre-calc again. So you don't have to worry about them being critical points. They were already ineligible to play. So for number 3, the critical numbers are x equals 8/3 and x equals 4. This number 4 is it for section 3.1. I have grouped section 3.1 and 3.3 together just because they're a little bit more related to each other. If I had written the textbook, I would have gone 3.1, then 3.3, and come back to 3.2. So that's the order that you'll see me teach it in case the lesson plans look a little strange this week. It's okay. There's a method to my madness. All right, find critical numbers here. A lot of people are going to look at this and go, uh-oh, quotient rule. I look at this and say, man, I'm rewriting it. This is actually just 6 times x plus 6 to the negative first power, and I don't have to do any quotient rule. I can just simply do, power rule. And there's not even a chain rule on it. Now, FYI, if you do quotient rule, it will work. It'll just be a few extra steps. Now, I don't want to do extra steps when not necessary, so I won't. Okay, here we go. Let's get a derivative. I got negative 6. X plus 6 to the negative second. Again, the chain rule would be times 1, which I don't need. I need to set that equal to either 0 or undefined. Let's rewrite it first. That's negative 6 over x plus 6 squared. Okay, so that's the first derivative. If I try to set it equal to 0 in the numerator, that completely fails. There's no way in the world that negative 6 will ever be 0. So yeah, okay. Let's go to the denominator. If you set that equal to 0, that will tell you where the derivative doesn't exist, which is also something that would spawn a critical number. And that would become x equals negative 6. So the critical number, there's only one of them, would be x equals negative 6. But before I circle it, I suddenly realize, wait a second. X equals negative 6 is the only number that was ineligible to play before I started. Negative 6 is not in the problem domain. So how can you call it a critical number when it's not even allowed to be there? So guess what? Find any critical numbers? There are none.
I find this next part to be just a bit strange.
I have to explain what it means to increase and decrease, even though that seems like complete common sense, and it really kind of is. But we have to formalize it because of what's going to happen later on in the course. So we'll start off with defining what it means to be increasing. A function's increasing if you start from x1 and you head to x2. And of course, notice in the fine print here, x1 is less than x2, which means x1 is farther to the left. That will imply, which means causes to happen, that f of x1, in other words, the y-coordinate right here, is going to be less than f of x2, which is the y-coordinate right there. In other words, you're rising. Okay, so that's the formal definition of increasing. Similarly, if I wanted to talk about decreasing, I could say, yeah, all right, same thing. x1 has to be less than x2, right? So it is. That will imply or cause to happen the fact that f of x plus 1, the original y-coordinate, is greater than f of x2, the new y-coordinate. So in other words, you are falling, you're decreasing. Again, that's the formal definition. I know that seems a little bit strange and useless, but we're going to be coming back to it. So there it is. Let's move on. Okay, hopefully this makes sense. I think we've already sort of seen it. Remember that derivatives function as slopes of tan lines and slopes of curves. So it makes sense that if the slope or derivative is greater than 0 or positive, then the graph is going to rise or increase. And sure enough, it does. Similarly, if the slope or derivative is less than 0 or negative, the graph's going to fall or decrease. We saw that in our sine charts before. And then obviously if the slope is 0, then you have a horizontal graph, at least for some period of time, and the slope is constant. And basically that's what I just said down here in my own words. First derivative positive, graph is rising. First derivative negative, the graph's going to fall. All right, so let's put this to work by doing some examples. Here in number 5, I just continued the numbering from 3-1, so this is number 5 now. Find the intervals on which f of x is either increasing or decreasing. Well, when you see increasing or decreasing, you want to use the first derivative. So let's take f prime of x. Which of course will be 3/2 x squared plus 3/2 x. If you want to know where a graph stops increasing and starts decreasing or vice versa, you need to make the slope, or in this case the first derivative, equal to 0. So that's what I'm going to do. That's also how you, of course, find the maximum and minimum values. So going to work now, I'm going to go ahead and factor out a 3/2 x from both terms, which will leave me with x plus 1 still equal to 0. And so my critical numbers are going to be x equals 0 and x equals -1. Now I'm going to go ahead and make my sign chart, and I'll put the 0 and -1 on it, and I'll test each region to see what's happening. All right, let's try a number from the left region. How about -2? And I'll just put it into the first derivative. I could put it in here, but it would be easier to plug it in right here. Which I don't need the equal 0 anymore. That was just to find the critical numbers. All right, -2 goes in. 3/2 times -2, of course, is going to be negative. A -2 into here will also be negative, and negative times negative is positive. And like we saw in the very last slide, if the first derivative is positive, the graph is rising or increasing. I like to show the graph going up. Some teachers will put a plus sign there instead. I like to show like an up arrow. It just gives me more of a visual effect, and I think that's kind of cool. All right, let's try a number in between -1 and 0. I'll go for -1/2. If I plug -1/2 in right here, the first parentheses will still be negative, but the second parentheses with a -1/2 is going to be a positive. And negative times positive, of course, is negative. If the first derivative is negative, which is what we plugged into, the graph's going to decrease or fall. There's going to be a max at -1, although we don't really care about that because the question didn't ask for that. We just want to know where we're increasing and decreasing. Finally, something larger than 0, I'll pick +1 this time. If you put +1 in to both parentheses, they're both going to be positive. And of course, positive times positive makes the first derivative positive, which means f of x will increase. Okay, so I've got a lot of good work. I have everything done except for the actual answer. I'm going to write that right now. And there it is. You can see that the intervals that it's increasing on would be the -∞ to -1, union with 0 to infinity, and in the middle it's decreasing from -1 to 0. I'll put that in red. Now, you may have noticed that I used hard brackets instead of curly parentheses here. And I'm going to apologize right now. I'm simply the messenger here. I know this is terrible. People are going to be like, whoa, wait a second, Mr. Lucy. You're telling me that at -1, you're increasing and decreasing at the same time. Yes, I am. I said that. And also at 0, you're going up and down simultaneously? Well, yeah, technically, yes. As strange as that sounds like, my grandpa saying that he, walked to school in knee-deep snow, uphill both ways. And I'm thinking, yeah, Gramps, no, I don't think so. But here, you have to use hard brackets. And the reason why is, if we don't, then this slide that we agreed was common sense a few minutes ago fails at the endpoints. So I know it seems weird. Again, like I said, I'm just the messenger here. You need hard brackets on both ends when you're talking about increasing or decreasing intervals. If it's concave up or concave down, which is something we're going to learn later, then you will use curly parentheses. But yes. Now, of course, notice that at -∞ and +∞, you're still curling those because you can't reach those values or those locations. So infinities and -infinities are always curled, no matter what the directions are asking for. So, all right, moving on. Okay, same instructions. Find the intervals on which the function's increasing or decreasing. That signifies the first derivative is necessary. All right, there it is. Once again, I want to factor, and this time I'm going to take out a -6x. And the resulting trinomial can again be factored into two binomials. Now, of course, we're looking for the intervals of increasing and decreasing, so we need to set the derivative equal to 0 because that's when it will change directions. And the critical numbers are going to be 0, -3, and +9. So again, it's time for a quick sign chart. And of course, we're going to use the easiest looking thing we can find to plug into that's still red, which obviously my eyes are drawn to the factored part. Again, I don't need this equals 0 there, that's just in the way. And I will try 4 different numbers. Let's try something from the far left. I'm going to try -4. I have 3 parentheses that I'm dealing with. I can put parentheses around this if I want to. All right, putting the -4 into the first parentheses makes negative times negative, which goes positive. The -4 will make the other 2 parentheses both negatives. Obviously, positive times negative is positive, If the first derivative, which was the red stuff, is positive, the graph will increase or rise, the graph of f of x. All right, moving to the next region. Let's try a negative 2. Putting a negative 2 in, again, this will stay positive. The middle one will go positive. Negative 2 plus 3 is going to be positive. And obviously, this will stay a negative on the end. Positive times negative, that's negative. If the first derivative is negative, the original graph will fall or decrease. You probably are thinking, oh, I see the pattern. It goes up, down, up, down. You have to be so careful about that. In this particular case, yes, it does. It alternates. However, let me tell you that that won't always be the case. And I will purposely make things that break this pattern to punish people to get lazy and don't finish out the problem the right way. So I'm just going to pretend that didn't happen for a moment. And we're going to finish the problem legitimately. So trying something between 0 and 9, I'll try positive 2. You can see that now the first parentheses becomes negative. The middle one is still going to be positive. That's 2 plus 3, that's 5. The last is still negative. 2 negatives, it's going to turn it positive again, so it will rise. And finally, if you try something larger than 9, let's say, what can I make this into? 42. Looks like a 42. You can see that with the first one, it's going to be negative, of course. But the other two will clearly become positives. Negative times positive, that's a negative first derivative. The original graph will fall. Okay, but like I said, don't get cocky here. All I have to do is throw an asymptote in, and I can make things go crazy. Or we can throw in some other things that you're going to see later on. Don't worry, there'll be plenty of counterexamples to this pattern. So you have to try all the regions. College Board is well aware of that as well, and they will do the same. Here's my final answer. Notice once again that the internal points, the negative 3s, the 0s, the 9s, are all hard bracketed. Obviously, the infinity, negative infinity will always be curly. So, again, you must hard bracket this on the test or quizzes. I will make a deduction if you do not. So, please don't lose the easy points.